Here we have the first question in this worksheet. This question is about electrical resistance. It says the heating coil is to be made of wire of diameter 3.5 times 10 to the minus 4 meters. The heat is to dissipate 980 watts when connected to a 230 volt DC supply. The material of the wire has a resistivity of 1.3 times 10 to the negative 6 ohm meters at the working temperature of the heater. Define electrical resistance. Okay, electrical resistance, this is the ratio of the potential difference. I'm just going to write like that, to the current. You could write it as R is equal to V over I if you explain what all the terms mean. Okay, 2. Calculate the resistance of the heater at its normal working temperature. Okay, so we have got its power here is 980 watts, and we've got its voltage here of 230. So we can use, here's the power, and we can use this formula. So that power is equal to V squared over R. Therefore R is equal to V squared over the power, and so we're going to get 230 squared divided by 980 watts. So we just calculate that on our calculators. 230 squared divided by 980, and we get 53.979. Now everything is to two significant figures, so that is going to be 54 ohms, like that. Alright, going on to here, show that the length of wire needed to make the heating coil is approximately 4 meters. So here we are given the resistivity, we're given the diameter, so obviously I'm going to be using this formula over here. We are looking for the length, so we're looking for this, I must change the subject of the formula. That length is going to be R times the area divided by the rho. Now you've got to be a little bit careful of this area here, in that we are given the diameter. So we're going to be using the area would equal pi r squared, so it's going to equal pi times 1.75, because the radius is obviously half the diameter, times 10 to the negative 4, and we're going to square this. Now obviously you'd be writing this all in here somehow, and perhaps even just putting that straight into your formula. So we've got our resistance here, we've worked out our resistance here is 54, so it's going to equal 54 times pi 1.75 times 10 to the negative 4 squared, and then we're going to divide that whole lot divided by 1.3 times 10 to the negative 6. We're going to do the whole lot on our calculators. So it's 54 times pi times 1.75 the exponent minus 4 squared divided by 1.3 exponent minus 6, and I get an answer of 3.996. so obviously that's equal to about 4 meters. Okay, now it's really important to put in to show your working, because if you make a mistake with that, you see you're given the answer here, so you've really got to show all your working, show you're changing the subject of the formula to get your 2 marks for that. Going down to this question over here, it says 3 identical heaters each provide power P when connected separately to supply S, which is 0 internal resistance. On the diagram, complete a diagram by drawing 2 switches so that the power provided by the heater may be either P or 2P or 3P. So what's important to remember is going to do another little thing here, another little diagram. If I've got two resistors like this, when I put them in series, say this is 2 ohms and 2 ohms, my resistance there, 1 over RT, is equal to 1 over 2 plus 1 over 2, which is equal to 1. So the total resistance is equal to 1 ohm. So basically you're halving your resistance when you're putting them in parallel. And because P is equal to V squared over R, when I halve my resistance, it's an inverse relationship. When I halve my resistance, I actually double the power. So we're going to be using that fact in solving this. So let's put them in. So basically what I'm trying to do here is, if I put in a resistor, there's different ways of doing this. There's a number, sorry, my line drawing's not too good. I could do something like this. I could put that in like that, and then I could have one open there like that, and I could have another one open like that. Now in this configuration you would have a power of, say, 3P. This would be the biggest power, because if I took this over here, if I close the switch over here, I'm actually going to halve the resistance, and so I'm going to get a less power. And if I close this, I'll even get less, because the resistance this would be, when I close this switch over here, I would get half the resistance, and when I close the switch here, I would get a third of the resistance, and therefore double the power and 3 times the power that would be coming out there. Okay, so that would be a possible way. You could also do it like this, another way that you could set it up. There's different ways you could do this. You could do something like this. You could have your switch coming in like that. There's a switch, and then you could also have another switch like this. So you could have it that you close this switch, and then you would have your lowest power, because you're going to have your highest resistance there, and then you could open this. You could open this one over here, and you could close this one. Could close that, and then you're going to have half the resistance, therefore double the power, and then you could close that, and that would lower the resistance further, and you could have 3 times the power. So that would also work. That would be another way of doing it. So the important thing there is to understand, from using this formula over here, which is, you have got your resistors in parallel. When you have more and more resistance in parallel, you actually lower your resistance, and therefore you increase the power, because your current increases. This is important to realize here. We have your I power is equal to I squared over R. So I squared is equal to power divided by R. So as you decrease your resistance, your current actually increases. The potential difference actually remains the same. In all of these cases, it would always be, say, 230 volts, but the current going through the circuit actually would increase as you lower your resistance.